right. Can you hear me all right? Great. So I'm going to talk about microservices, building microservices with Vase and Linkerd. But before we get into that, I almost feel like I need to apologize for speaking about microservices, given the amount of inflated expectations connected to this topic. And if you believe this Google graph, it's still going strong, but I think many people have become a bit more cautious about this approach. And many people who have been in the industry for a while might say, well, isn't that just service-oriented architecture in its second coming? And while I understand where this sort of idea comes from, and I also think that it's sort of a new thing in its own right to speak of microservices. And that's not only because services-oriented architecture is associated with maybe some problematic technology choices that have been sold in its name and have sort of blurred the ideas behind it, but also because I believe that the foundations of what we call microservices, there is something genuinely new there. So there's starting from sort of the basic building blocks in automated infrastructure to sort of the ideas around sort of what I would call technical scalability. But the one aspect that interests me most in the context of this talk is sort of the social aspects of building microservice systems. And so whenever we write code, we communicate with machines, of course. But I think to the same degree, we also communicate with other people through that code or in the establishment of writing that code. And that's why the sort of constraints that apply to us communicating as humans in social systems sort of bleed into the technical systems we build and design through code. Now, this insight is nothing new. And actually, Melvin Conway has had quite a bit of screen time already today. So he wrote this paper in, I think, 1968, How Do Committees Invent, where he sort of formulated this idea that that the organizational structure and the way they communicate, he called it lead to direct copies of these structures in the systems that are designed by these organizations. And this idea from this paper has been popularized under the name Conway's Law ever since, and you've probably heard about it already. And there is sort of a trivialized example that's often cited in this context, and I'm going to repeat it anyway. If you have an organization with 4 teams and you let them build a compiler, you end up with a 4-pass compiler, sort of to illustrate some of the ideas behind it. And I think what this tries to say is that the output of that design process is not necessarily optimal in a technical sense. And I think there's also some good empirical evidence to support this idea, or Conway's law, and there's also some good intuition why it might be true. I mean, we all have experienced that, how much easier it is to communicate within a close-knit team of developers, and how much harder it is to sort of go outside your comfort zone and establish common interfaces, APIs, or something across a large organization. Contracts, design ideas, things like that. Now, what I find interesting about microservices is that it sort of turns this law upside down by saying, let's build systems composed of many, many small, relatively independent components that are loosely coupled. And that sort of is very well aligned, maybe, with an organizational structure composed of many, many teams that work in relative autonomy at maybe even different speeds. So the design in some way, the technical design of the system in some way might mirror the organizational structure you have. It doesn't say that that's necessarily then the best technical design, the output of that, but at least there's sort of an alignment here. And there's one other sort of aspect that I find important or interesting, and that's sort of a matter of scale. So in the same way as concepts that work in the small don't necessarily work well in the large, you can't scale an ant to human size. I think in similar ways, it is probably true that concepts that work well in the large don't necessarily translate into the small. So if you're just 3 people building a system, you probably won't experience many of these frictions or these problematic situations that might drive you towards such an architecture from a social point of view. So the question is, sort of, where's the boundary? Where does it start? Is it a matter of the size of the organization? Probably not. It's more sort of a combination of maturity, of processes, and of also technical, of course, needs. Do we actually need that? So what I'm trying to say here is there's a good chance that you don't need a microservice architecture. There's a good chance that you are totally fine with a well-structured monolith, and that could be the end of this talk. And but let's assume we had to build such a system for the sake of the argument. And just to give you some background how I came to this topic, I recently switched jobs, and I was previously working for a company where I joined in the last couple of months while I was working with them a team of developers who were building what I would call a microservice platform in disguise. Basically, data transformation pipelines built up out of small independent components that were interacting. And they were very ambitious. So they built everything themselves from scratch, including their own programming language. So when I joined them, I was a bit skeptical, and I started evaluating, options or ways to fight the not invented here syndrome a bit. So I was very curious when earlier this year a beta version of Vase was announced as an open source library, because it seemed to fit exactly that spot that we were working on. Now, I'm not going to go into too much detail about Vase here. There are excellent talks by its creators that I recommend you watch, or even better, maybe you try it out yourself. It's very easy to get started. But I want to mention a few points in case you don't know the library, and also sort of set up the rest of the talk. And I want to do this in 2 parts. I want to take apart the tagline of Vase, which is data-driven microservices, and look at the data-driven aspects first, and then later at the microservice part. So what Vase does in one sentence is it allows you to build very simple services fronted by an HTTP API backed by Datomic. And I'm tempted to say CRUD services, but I'm not entirely sure if that's really true. And the idea is that you don't build them in code primarily, but that you define them in data, in an Eden file that you construct. And this is an example of an empty service definition. I've put it up there because I think it illustrates quite nicely the foundations of Vase as a library, because it's sort of built, it sits on 3 pillars, if you will. There is pedestal routes to define the entry points into your service. You can define as you would in pedestal. Then you have closure spec to validate and conform data that's transformed through these API endpoints. And finally, you have Datomic schema to describe the shape of your data in Datomic. And then Vase has this idea of versioning, so that you can have multiple versions of APIs in that same sort of Eden document. And you can have multiple versions of these APIs active, or you can deactivate them as you see fit. Now you have this Eden document, and the next question is, how do you turn this description of your service, this data description of your service, into a running, living thing? And for that, you have to know that Vase has this idea of a container, and you can roughly say that's basically everything that pedestal runs on. And you somehow have to get it in there. And this is this arrow that I've drawn on that slide. And in the first versions of Vase, and that's what got me interested because it directly matched our use case, you were able to dynamically spin up these services by just posting your Eden document to a sort of API of APIs, a mother of all APIs, that would then instantiate your service in the container. And this functionality has been removed. I think it can be reinstated if you needed that. And what you now typically do is you sort of bake it into your jar file as part of your build process and ship it with that. So to recap, what Vase does, I think it's a good idea to have a look at the mission statement. The design document of Vase in the GitHub repo sort of outlines that. So the basic idea here is to remove the incidental complexity that you experience when you build these very simple services with HTTP APIs. So as a fast way of building prototypes, of trying out new ideas, to get to deliver faster. I think that's it's emphasized very strongly. But at the same time, being flexible enough and open enough to evolve this service into another direction if it's necessary. And then the last point that's mentioned in that design document is production quality. And I got a bit hung up on that because I was wondering what does that mean? How is that production quality, or what does production quality mean in the context of such a library? And I think you can approach this from various angles. You can think about the various deployment options you have with Vase. So being based on Pedestal, you can deploy it inside a Tomcat, a Jetty, a Mutant, I don't know what. You can approach it from sort of the security point of view, that you can say, well, we inherit all the security features that exist in Pedestal as well. But I don't want to answer this question right away. I want to sort of put a pin in that and come back to that question later once we have looked at the microservice part of it. Because what does turn a library into a microservice library? I think there are many ways to think about that. You can sort of come from a domain-driven design perspective and talk about single responsibilities and bounded contexts and aggregate routes. But if you look at sort of the deployment sort of architecture, high-level view, then you can also deploy Vase in a very conventional sense behind maybe some kind of edge service, maybe a reverse proxy, some TLS termination or what have you. Of course, you have to keep in mind it's based on Datomic, so you have to have a production quality Datomic deployment somewhere in the background, but I'm leaving that question out for the purposes of this talk. But in my mind, I think, so when we think, what sort of makes it a microservice thing is that you break up something that used to be sort of in-process function calls and turn it into multiple components that talk over a network to each other. And with that, we are sort of in the space of distributed systems. So when we're talking about microservice libraries, I think we have to approach them as building blocks for distributed systems. And then maybe that diagram changes a bit. Maybe look like this. So even if you have a very simple system that you want to build, I think it's not far-fetched to say there's at least something in front of a Vase service maybe that does authentication or authorization. And then there's this big question of whether you can get your design, your domain model down to such a clean and isolated, sort of from a responsibility point, state that you can avoid talking to other services. But is this really realistic? Can you really expect your teams that build this architecture out of many, many components to not call into other services? I think probably not. And then the next question is, of course, what does Vase offer here? And the answer is it's not really primarily built for that. So shelling out or integrating with a third party. And this is just a listing of the reader literals that are built into Vase. So you can respond to a request by calculating some kind of response. You can redirect to another URL. You can conform data using ClojureSpec. You can query data that sits in Datomic, and you can transact new data into Datomic, and you can, again, validate using ClojureSpec. And then the next one, intercept, is sort of a wildcard in a way that allows you to do anything. And through that sort of backdoor, we can, of course, get in this third-party service integration or calling out to other services. Maybe not in this way, sort of by testing the limits of what you can do in Eden and trying to squeeze in some Java interrupt to shell out to another service. But you don't have to do that. You can simply write a normal pedestal interceptor, some Clojure file somewhere in your project, and reference that in your Eden service description. But there's sort of one interesting consequence of that, because if you do that, if you sort of enrich what pedestal, or in this case Vase, does for you by writing own interceptors, you leave sort of the the realm of a self-contained service description. You suddenly have now this problem of dependencies. You need to sort of pull in that code somehow wherever this service is going to be deployed. You cannot simply send this Eden file somewhere and run it or turn it into a service. You have to somehow get the closure code there. And that's typically shipping a jar somewhere, unless we come up with a better, more flexible way of breaking down these artifacts in smaller chunks. And of course, there are other ways. We can extend Vase itself. We can add new reader literals. But I think it comes down to the same problem that you have to ship some additional code. And having said all that, I think we can now return to that question of production quality. Again, now that we have sort of built a lot of these Vase services, or maybe other services as well. And for me, then, two new sort of questions come up that need to be answered, or concerns. And these are observability and resiliency in a distributed system. So with that, I mean, as you all know probably, observability, we want to see what's going on in this sort of mesh of components that interact by aggregating any diagnostic output they produce in a central location to see what's going on. By maybe distributed tracing to see as requests go through this mesh of services, if something goes wrong, that it doesn't turn into sort of a forensic investigation to find out where it went wrong and why. And maybe also just regular telemetry data to see what's happening before things go wrong. And on the other hand, sort of in the resiliency corner, we need to deal with failure, partial failure, and well, easy, we'll say. Well, if a request doesn't work to another service, we just retry. How hard can it be? And I've seen code similar to that in productive scenarios a couple of times, and we all know it's not that easy, right? We need to sort of think about exponential backoff so that we not make the problem worse by hammering a service that's already struggling. And not even that is enough. We want to introduce jitter. So I'm not trying to educate you here about how to do retries. I think the point I'm trying to make is that these problems are, I would say, non-trivial and need to be addressed in a sort of production quality manner. And if retrying doesn't help, we have already had on the first day of the conference the mention of circuit breakers to isolate, at least temporarily, a component until it recovers. Again, we need production quality implementations of these. So what does Vase offer in that respect? And the answer is nothing. And that's not bad. That's not a problem. I think it's completely out of the scope of that library. But when we think about deploying that in sort of a productive environment, we need to address these issues. And there are many, many ways to address these issues. And this is a bit arbitrary sort of stream of consciousness graph that I've made up with random technology names below the fold. What are our options? So these problems have been solved in many ways. And of course, we can now say, on the one hand, let's just offload all that, or at least parts of that responsibility to a vendor. Let's just deploy that service in a platform as a service. And we get then some of the observability back, or we might even use one of the newer function as a service things like Amazon Lambda. And as far as I know, the creators of Vase are actually working on that, sort of making Vase a first-class citizen in a sort of a Lambda environment. But even if we don't want to do that, if we go back to the more traditional conundrum between frameworks and services, then I think we can all get very excited about how bad frameworks are. In my mind, it's always, some people have thought very hard about these problems that these frameworks try to address, and they have come up with very good answers in most cases from their point of view for all of these problems, usually with one answer to each of these problems. And the problem is that maybe these answers don't match your use case or your needs, and then these frameworks can turn into sort of a straitjacket. But on the other sort of implication is that there's often they draw you into a sort of a language environment as well, especially if you go down the road of these frameworks I've listed here, which might not be ideal. So as a closure sort of programmer, you might be more tempted to use a library, and there are high-quality libraries that address the concerns I've listed. Organizations like Netflix have been doing this for years. There's things like Hystrix, it was already mentioned yesterday, with closure bindings and stuff like that. But I want to remind you of what I said in the beginning about the social implications of building these kinds of microservice environments, that we want to have independent teams, have a relative high degree of freedom to build their systems at their own speed, maybe. And now we're reintroducing a shared code base, a library. And suddenly we have to maybe upgrade that library because there is a, I don't know, security issue. And we have suddenly to introduce sort of a coordination point across all these teams that are sort of theoretically fully independent or relatively independent. It's not impossible, of course. It's perfectly doable, but it sort of wraps the whole idea the wrong way a bit. So what I've learned recently, that there's another way. That's what I'm going to talk to you about today. And it has various names. It's sometimes called a service mesh, a service proxy, and one of the projects in that space that is Linkerd, which is what I'm going to talk to you about today. And there is more recently a thing called Envoy has been released by Lyft. It's sort of in the same space and addresses similar concerns. For this evaluation, I went with Linkerd because it sort of integrated more closely with the environment we were targeting, which is Kubernetes. But I'm not sort of advocating one or the other. See this as an example for a class of solution, class of product, rather than as a recommendation. So Linkerd, the name is a bit inspired by the linker from your compiler toolchain, but instead of linking object files and libraries, it links services talking over network to each other. So it's a transparent proxy. And from a technology point of view, it's based on Twitter Finagle. So it's Scala. Netty is in the mix. And if that makes you run for the hills for one reason or another, don't worry, it's out of process. So the deployment scenario here is similar to that. So as I said, we were targeting Kubernetes, so you would have some containerized version of your service somewhere. And then Linkerd sits typically next to that application, wherever you're running it. And because that's basically a sidecar container. And because it's a JVM thing, it has some significant memory requirements. So the recommended way to deploy this in Kubernetes is what they call a daemon set, where you have just one instance on each node, and all the Vase services in this example that need to do network I/O talk through this one instance. So you minimize the memory footprint and trade in a bit of availability here. And the idea is that you have this across the board, across all your services. And the Linkerd components sort of route the traffic from these services coming in to other services and back. And also it can also do, to some extent, ingress and egress out of the whole cluster. And the information where to route and where to find the other services comes from another component called Namerd, sort of a dynamic store for all the routing information that integrates with your service discovery mechanism. So what you get by doing that is you get exactly these things that I listed. That's why I listed them. You get retries, you get a sensible and production-proven implementation of backoff, because that's all Twitter Finagle in the background. You get routing that integrates with your service discovery mechanism via these rewriting rules or delegation tables, I think they're called in Finagle. It's just a rewrite of a function from your host name to a lookup in the Kubernetes service discovery mechanism to find a service with the same name. And then it routes traffic to one instance of that service. And if you think back at what I said about sort of Vase as a tool to rapidly prototype, to try out new things, I think it's quite well with Linkerd because it has quite advanced capabilities when it comes to traffic shifting. So you can do canary deployments where you route, like in this example, 10% of your traffic to one version of your service and 90% to another. And you can go even more dynamic by controlling the traffic via individual headers or special cookies if you want to expose a new version only to a very, very limited population. So Linkerd addresses the concerns with regards to resilience. We we get service discovery, and it's not, because I mentioned Kubernetes, it's not sort of limited to Kubernetes. It's fairly neutral when it comes to where and how to run it, and integrates with various backends. You can do nice things like transparent TLS between your services without having to integrate that into the service implementation, and you get also benefits in tracing and telemetry. I'll talk about that in a little bit. So on the practical level, how does that work? Well, it's a transparent proxy, and it's actually a HTTP proxy. And why is it an HTTP proxy? Well, in order to implement a circuit breaker that recognizes if something goes wrong, HTTP status codes are sort of a good way to find out if something goes wrong, unless you get no response at all, of course. So that's why you have to configure a HTTP proxy in your application. It's readable, yeah. And there are system properties in Java from that to do that you have to set. And then it depends on what kind of sort of library you use to do your HTTP requests from inside your service. If you use things like CLJ HTTP, it will transparently pick these properties up. If you use anything that uses NIO, the new non-blocking IO stuff, it won't pick up these properties. I think it depends on the author of the library whether they integrate support for proxies. And that also means you have to do a code change, because the other thing was just a startup parameter, and now you have to sort of pass these proxy settings through when you create the client. That might be might or might not be a problem. But I think it's a fairly limited sort of contact surface between the two things. And if that doesn't work, there are alternatives. You can do crazy things with IP tables and stuff in Kubernetes to sort of get around the whole idea of setting up these proxies in your application. Let's look at the second aspect, observability. Well, we get some immediate benefits there. So without sort of implementing any kind of metrics or application metrics, I'm not saying you shouldn't do that, but we get some basic metrics across the board, unified metrics from these Linkerd instances that sit next to every service. And we can then feed them into whatever monitoring solution you have. For example, I don't know, Prometheus, or I think StatsD is also supported. And we get some insights into the state of the system that go beyond connection level sort of metrics. Because, as I said, it's request level. So we know failure rates, we know how many requests go bad, we see the latencies and things like that. And there's also a very basic dashboard built into Linkerd itself to get you started. And on the front of distributed tracing, what we can do is we can integrate with tracing tools like Zipkin, for example, to see how your requests go through your services. Again, on the practical side of things, you have to pass through these tracing headers that Linkerd uses internally. And Vase actually has explicit support to configure. This is, again, a snippet from that Eden service definition that I mentioned in the beginning. You can configure explicitly to pass through certain headers, and that enables this distributed tracing if you use it in combination with Linkerd. So one implicit assumption that I've made, and I've not really made explicit, is that all the traffic we have in that system is sort of synchronous HTTP-based traffic. Now, if you listen around what people are saying, you will find quite strong proponents of, event-driven message passing architectures, asynchronous message passing, and there are good reasons. I mean, if you do synchronous HTTP between these services, we introduce a temporal coupling between the services, of course. So A and B, A talking to B, both have to be, at least in one instance of them, has to be alive. We also use resources to maintain, if you do multiple requests to multiple services, you need to maintain these resources, network, whatnot. And of course, we have also this problem of sort of accumulating latencies if we build deeper chains of these services from service to service call. But I'm not going too deep into this sort of question of whether you should now switch from a sort of synchronous HTTP approach and redesign your whole system into an asynchronous message-driven one. I just want to point out two things, basically. First, of course, that the tooling I've just introduced or presented to you doesn't work as well, is not as expressive once you go away from HTTP traffic, because you don't have the same insights into a binary wire protocol. You can still have some basic metrics on the connection level, of course, with TCP traffic, for example. And the other thing I sort of want to mention that I believe is, I think it's not that black and white. And in my experience, at least, there will be almost all the time a mixture of both. At least as an external interface, as the least common denominator that everyone understands. And even if you want to sort of, even in between that, there's still some gray areas where you can say, yeah, we can even go into a sort of more event-driven, asynchronous architecture using HTTP. You know, we shouldn't conflate the connection protocol with the way we do we design the sort of general architecture of how communication works on the application level. We can send messages, we can listen to events, even over HTTP traffic. But as I said, I don't want to get too deep into that, because I think that's a completely different talk. And you already might have the impression, even without introducing now a distinction between sort of outside traffic through synchronous HTTP and inside asynchronous event-driven, you already might have the impression that we're building a massive Rube Goldberg machine here. There's a lot of complexity, a lot of moving parts here. And I would say incidental complexity, because I've never mentioned any use case, any domain, any problem domain here. If you watch the examples, they were all really trivial hello world examples. So all this thing that we sort of built up is, all the complexity we've built up is incidental, but sort of required incidental complexity if we want to have these properties of destructuring the system in the way I've described it. But I think all is not bad. At the same time, I think we've discovered that there's an interesting orthogonality between these concerns that I've sort of flagged up. There's this ability to maintain the properties we like about a library like Vase, to be able to iterate quickly, to prototype, and still embed it into sort of an environment that's production ready or has production quality. And we can do that because we use a tool like Linkerd. It's sort of loosely coupled with the applications or services it hosts through a well-understood protocol like HTTP. So we can actually, we must not despair, I think. It's a viable sort of way of building things. And I think that's more or less all I've had. So thank you very much for your attention. And if you have any questions, I'm happy to take them.